So welcome students. So today's class we will study about the packed bed column, the flow through the packed bed column. So packed bed columns are the a important phenomena which is generally studied in the chemical engineering. It is related to the reaction engineering. So in the reaction engineering, generally when you are doing the heterogeneous reaction, we can use the solid catalyst. So these solid catalysts are generally these solid catalysts are generally inside the a column. So this is the diagram of a heterogeneous reactor. So these are the solid catalysts. So these are the particles in the particulate form or in the granules form. So these are the solid catalysts. It is filled in a column, and the generally reactants comes as a gaseous phase or liquid phase. If the reactant are in the gaseous phase, so it will comes from the bottom of the column, enters the column from the bottom and moves from bottom to upward side, then removes from the upward of the column. If it is a liquid type reactant, then it will move from the top to bottom. Okay, so this fluid exerted the force on the catalyst. So we will discuss about how much force will exerted this type of catalyst. So why this is important? Because it will used to design this type of column. Because if the catalyst force is much higher, then catalyst will start to move with the gas, and if force is lower, then it may be the pressure drop may be significantly high, then you may not get the exact amount of the gas cannot be passed through from the column. Okay, so you have to maintain the flow rate of the reactant in such a way that it will successfully passes through the column, and it may not take the catalyst with itself. Okay, and sometime we can also use the other types of column where we can use the moving bed. So it is called a fluidization. In fluidization, we make the reactors in such a way that the catalyst start to move with the reactant. So it happens when you have to regenerate the catalyst, so you have to continuously remove the catalyst from the reactor and regenerate it, and then again feed in the column. Or sometime it will also increase the area of the catalyst, because in the heterogeneous reaction, rate of reaction depends upon the surface area of the catalyst, or the conversion will depend upon the surface area of the catalyst. So if catalysts are in the suspended form, or it is flowing with the reactant, then you have the more reaction time and you have the more reaction area. Okay, so both type of design we will study in this for both type of design we will study the flowing phenomena. Now come to the course. So first we have to define some different factors which is used in the flow in the packed bed. So first is the first is the porosity. Okay, so this size represent the porosity. So it is defined as the volume of the void in the bed divided by total volume of the bed. Okay, so it can also calculated as the total volume of the bed minus the volume of the solid divided by total volume of the bed. Okay, this is the porosity. The next characteristic which is defined as AV. AV is the specific surface of a particle. So AV can be defined as SP by VP, where SP is the surface area of particle and VP is the volume of the particle in meter cube. Okay, so SP by VP, the unit will be 1 by meter or meter inverse. So it is called the specific surface of the particle. Now the next for if the particle is perfectly spherical, then this will be equal to AV will be equal to 1 by dP, where dP is the diameter of the particle. Okay, for a packed bed with non-spherical particle, dP can be calculated as 6 by AV. From this formula we can calculate the dP for a non-spherical particle, that will be equal to 6 by AV. So this is the formula of dP. Okay, so here we again define one more characteristic, which is A. A is the ratio of total surface area of the bed to the total volume of the bed. So it is the ratio of the surface area present in the bed or the surface area available for the reaction divided by the total volume of the bed. So it is very useful in the this property is very useful in the reaction engineering for calculating the overall conversion. To A equal to AB multiply 1 minus xi, where xi is the porosity of the or the void or the porosity of the fixed bed reactor. So this is equal to 6 by dp, because AB equal to 6 by dp here for the spherical particle, multiply by 1 minus xi. Now this is the example where we calculated the different properties. First, the porosity, void fraction of the porosity. Porosity is also called the void fraction. Okay, so both are the same term. In this book, it is written as the void fraction. In some other books, you will find it is as a porosity. So this is the volume of void bed divided by total volume. So here they have calculated the porosity. Then they calculated the SP, value of SP, and then calculated the VP. So, and from VP we can calculate the AV and DP. Okay, then we calculated the value of A. So this is the example, simple example. Now again the next parameter is the superficial velocity. So basically the superficial velocity is the velocity when the velocity of fluid when we assume that the column is empty. So this is the superficial velocity. This is not the actual velocity. Actual velocity is V. Okay, here actual velocity is V. It is a linear velocity, linear average velocity of fluid inside the packed bed column. Okay, so in this diagram, when the fluid flows from here to here, okay, so what will be the average velocity of fluid? Okay, so that is called the, that is represented by the V. So it is the velocity, actual velocity when this column is filled with the particles. Now we can assume a superficial velocity which is the same volume, which has the same volumetric flow rate, but the column is when the column is empty. Okay, so that can be calculated by V dash. V dash is the superficial velocity, that is equal to xi, which is the porosity or void fraction, multiplied by V. Okay, the next parameter is the hydraulic radius. Hydraulic radius we have already defined in the closed channels. So hydraulic radius equal to RH. It is represented by RH. RH is equal to cross sectional area available for flow divided by the wetted perimeter. So here the wetted perimeter is overall parameter or overall surface area of the bed, that is the wetted parameter, means the circumference which will be wetted by the fluid. Okay, so that can be this can be written as the void volume available for flow divided by total wetted surface of the solid. So here we multiply by the a linear parameter, so it will become the volume, it will become the total wetted surface. Now divide by the volume of bed, both parameters divided by the volume of bed, it will become xi by A. So RH equal to xi by A, where xi is the void fraction or porosity and A is the ratio. What is the A? A is the ratio of total surface area of bed to the total volume of bed. Okay, now RH, if you use the, if you substitute the value of A from the above formula, from here we have calculated the value of A as 6 by dp 1 minus xi. If you substitute this value of A, then you will get the RH equal to xi by 6 1 minus xi dp. Okay, so here we get the value of RH. Now D equal to equivalent diameter, D equal to 4RH, that we have already discussed. So when you know the value of D, this is the equivalent diameter, you can calculate the Reynolds number of fluid. This is the Reynolds number of fluid and this is the Reynolds number of particle. So Reynolds number of fluid equal to 4RH V rho by mu, where RH is the hydraulic radius, V is the velocity of fluid, rho is the density of fluid, mu is the viscosity of fluid. So when you substitute the value of V as a xi V and you substitute the value of RH equal to xi by 6 1 minus xi dp, then the substitute when you substitute these two values, you will get this value as a Reynolds number, 4 by 6 1 minus xi dp v dash rho by mu. So this is the value of Reynolds number when in the packed bed. This is the Reynolds number of fluid in the packed bed. Now similarly you can calculate the Reynolds number of particle, that is equal to NREP, that is equal to dp g dash 1 minus xi mu. Here v dash is the superficial velocity again, and dp is the equivalent diameter, 1 minus xi, xi is the porosity or void fraction, mu is the viscosity of fluid, rho is the density of fluid. Now for, as we know, we can use the Hausen-Pauli equation for the Reynolds number for the laminar flow. So when you use the Hausen-Pauli equation, that is the pressure drop across the column should be equal to delta P equal to 32 mu V delta L by D square. So this formula we have already developed when we use the when we solve the problem for the laminar flow in the tubes. Okay, so this formula arises from there. So here we just substitute the value of v equal to v dash xi, okay, and then substitute the value of d square equal to 4rh square, and rh equal to this xi by 6 1 minus xi dp. When you substitute the value of all this value, you will get this value 72 multiplied by mu v dash delta L 1 minus xi square divided by xi cube dp square, where mu is the viscosity, v dash is the superficial velocity, delta is the L is the length of the column. So in this formula we are calculating the pressure drop across this column, how much pressure drop occurs across this column when fluid flows from the bottom to upper part of the column in the fixed bed. Here bed is not moving, so you have to maintain minimum that pressure. When you, for that is the pressure drop, so you have to give the more pressure from here to achieve to transport the gas from here to here. Otherwise this is the pressure drop. Otherwise if the value of pressure is less than the value of pressure drop, then the gas will not transport from here to here, okay, from bottom to upper part of the column. Now from this formula, this formula we can calculate the value of the delta P, that is the pressure drop. So this is from the Hausen-Pauli equation. But when we do the experiment with the different experiment, when we do the experiment with different value of xi and different value of mu and v dash, then we will find that delta P is actually in the when the Reynolds number of the particle is less than 10 and the void fraction is less than 0.5, then this 72 factor is actually the 150. So this is the theoretical result and this is the experimental result. When we have done the experiment, we have find that this formula is not correct. So here the constant 72 should be actually 150. So why? Because this formula comes from the Hausen-Pauli equation, and Hausen-Pauli equation is developed from the flow in a tube, in a empty tube, and here we are solving the problem for the fixed bed. The bed is filled with the particles or the granules. So here the same formula may not be correct, and here this 72 value should be 150. Okay, so here the formula is same, just we have substituted this, we replace the 72 to the 150. So this is the correct, this the formula, and it is called the Blake-Conzi formula, and this formula is true when the Reynolds number is less than 10. Okay, here delta L is the length of the, basically length of the column. So delta L is the height of the column, height of the packed bed, here to here. This is the delta L from here to here. Okay, now this is for the laminar flow when the Reynolds number is less than 10. Basically in the Stokes law reason, Stokes law is applicable when the Reynolds number of particle is less than 1, and it gives the significantly correct answer when Reynolds number is less than 10. So basically this formula is true for the Stokes law reason or creeping flow reason. Okay, and if the flow is the turbulent, then you can use this formula. This formula is true when the flow is turbulent and Reynolds number of particle is greater than 1000. So this formula is true when the Reynolds number is greater than 1000. Okay, Here f is the friction factor, 3f rho v dash square delta L by dp 1 minus xi by xi cube, where f is the friction factor, other parameters are same as written here. Now in this formula f can be written, when we have done the experiment, we found that 3f equal to 1.75. It is a constant value. So in the fixed bed reactors, 3f value is constant, friction factor is constant, and 3f is equivalent to 1.75. So we replace the 3f to the 1.75, then delta p will comes as a 1.75 rho v dash square delta L by dp 1 minus xi cube, where rho is the density of fluid, v dash is the superficial velocity, delta is the length of the fixed bed reactor, dp is the equivalent diameter of the bed particles, and 1 minus xi is the porosity of the bed and or the void fraction of the bed. Okay, so this formula can be used when your NRP value, when the Reynolds number of particle is greater than 1000. At that time we can consider the turbulent flow. So this value is for the packed bed reactor. In the flow in the empty channel anti-tube, the turbulent region arise after 4000, but in the packed bed reactor the turbulent region arise after 1000, or and laminar region will be in the packed bed reactor less than 10. In the empty channels, Reynolds number for laminar flow, Reynolds number should be less than 2100, but in the packed bed reactor Reynolds number should be less than 10. So you should understand the difference in the both phenomena. Okay, now if you have the intermediate region, that means the Reynolds number is greater than 10 but less than 1000, then you can use this formula. This is basically nothing but the summation of the both formulas. Okay, so this experimentally we found that this formula is significantly correct when you have the Reynolds number less than Reynolds number less than 1000 but greater than 10 in the transition region, not in the laminar region, not in the turbulent region. Okay, this formula is called a Burke-Plummer formula. Okay, and this is the summation of the both formulas, in this formula and this formula. So this formula is true when the Reynolds number is less than 10. This formula is true when the Reynolds number is greater than 1000, and this formula is true when the Reynolds number is greater than 10 but the less than 1000. Okay, equation 3.120. Okay, this is nothing but the rearrangement of the formula in terms of dimensionless group. So you need not to remember this. You also need not to remember this if you want to use, but for the exam purpose. But if you want to use these formulas for the future study, or if you want to go for the some competition exam related to the chemical engineering, then you have to remember this formula. These formulas are very important in the competition exam purpose. Now this is the example where we have used the formula to calculate the pressure drop. Now one more characteristic which is used in the packed bed is the shape factors. So shape factors are very much used in the chemical engineering for designing the different equipments where we use the particles or granules or similar catalyst. Basically the shape factor represent the sphericity of the particle. It is also called the sphericity factor. Okay, so generally we know that the granules or particles are irregular in shape. It is not the sphere, it is not the rectangle, it is not the cubical shape, it is not the cylindrical shape, it is the irregular shape. So we compare the shape of the particle with the sphere, how much spherical particle is. So that is called the shape factor. So how we define the shape factor? So shape factor of a particle is the ratio of the surface area of that sphere which has the same volume as the particle to the actual surface area of the particle. So suppose the volume of the sphere is Vp, Okay, volume of the particle is Vp. So you can calculate the volume by the water displacement method or fluid displacement method. So once you know the volume of the particle, then you can calculate the that volume if the that volume is equivalent to the volume of a sphere. So the formula of the volume of sphere is pi d cube by 6. So this is the volume of the sphere, and surface area of the sphere is p is equal to pi dp square. So the sphericity should be pi dp square by sp. Okay, pi dp square is the surface area of the sphere, and the actual surface area of particle is sp. So this is the ratio of this is called the surface shape factor or the sphericity factor. Okay, phi s. So phi s can be defined as pi dp square divided by sp, where pi dp square is the surface area of the sphere which has the same volume as the particle, and sp is the actual surface area of the sphere. Okay, so once we can define the different characteristics which we have earlier used in terms of sphericity. So sp by vp can be defined as that is equal to a, the sp by vp can be defined as 6 by phi s dp. So this is the uh, uh, this is the way to return the ratio of sp by vp. Sp is the surface area of the particle, vp is the volume of the particle. So it is called AB also. So AB equal to 6 phi s dp, and A can be written as 6 by phi s dp 1 minus psi. So it is nothing but we have just substitute the value of phi s from here, from this formula to the actual formulas which is given earlier. So here, okay, so here AV is defined as SP by VP and A is defined as AV 1 minus psi. So here just substitute the value of phi s in the SP and you will get the exact value. You will get these formulas. Okay. Now if you have the mixture of particles, then specific surface area AVM can be defined as mean specific surface area is the summation of xi AVI, where xi is the volume fraction of the different size of particle, and AVI is the specific surface of the that particle. AV is the SP by VP. So SP is the actual surface area of particle, VP is the actual volume of the particle. So you can calculate the AV value of AV for different material size of particle or the shape of the particle and multiply it with the volume fraction of that particle. So if you have the mixture of different types of particle, you can use this formula to calculate the mean specific surface area of the particle. Okay, so this is the example where we use the mean, we have calculated the mean specific area dpm here, and then calculate the mean specific diameter or equivalent diameter. Now we will also discuss a most very important law, that is called the Darcy empirical law. So in Darcy laws, this is very important law in for the laminar flow region, and it is widely used to calculate the pressure drop. So this is the simplest law. You have find that the formula we have discussed earlier for calculation the pressure drop, these formulas, these are the slightly complicated formulas. Okay, so in the laminar region we can also use very simple formula which is called the Darcy law. So Darcy law is actually developed by experiments and observations only. So this is called the empirical law. So in Darcy laws, v dash is the superficial velocity, is the proportional to the pressure drop per unit length of the column. Okay, so in the Darcy's law, the superficial velocity, if the flow is in the laminar region and the flow is very slow, very slow, okay, then the flow rate is very small actually, then the v dash or the superficial velocity is proportional to the pressure drop per unit length of the column. Okay, so v dash is proportional to delta p by delta l, and when you remove the proportionality sign, a constant will come which is represented by K by mu. Okay, where mu is the viscosity of the fluid, okay, and K is a new parameter which is called the permeability. Okay, permeability of the fluid inside the column. Okay, so this is generally used when you have the very low flow rate. Okay, so it is generally used when you do the experiments, when you just put the water in the dense powder. Okay, and water is slowly moving inside the column, then you can use this formula for calculating the pressure drop across the column. Okay, so this is all about the fixed bed characteristics. In next class we will start with the flow in fluidized bed.